Good morning, everyone who's just joined us bright and early today, 8 o'clock webinar, just to make sure you're awake. Awesome. Are you ready to get started, Phil and Jeremy?
Yeah, I think so. Yeah.
Yep, let's do it.
Beautiful. No problems. Well, again, good morning, everybody. My name is Bianca, and I'm the Outreach and Engagement Team Leader here at Master Builders. I'm delighted to welcome you all to today's webinar. Before we start, Master Builders acknowledges the traditional custodians of country throughout Australia. We pay our respects to elders past, present, and future, and we embrace our shared future. Before I hand over to Phil to introduce Jeremy, who's our presenter for the day, just a few housekeeping things for you all. As you know, this session is being recorded. You would have gotten a little warning at the start of the webinar. We encourage you to keep yourself muted throughout the session while Jeremy is presenting. And all questions should be directed through the little quick Q&A box at the bottom of your panel. We'll go through those questions actively as we go through the webinar. Again, thank you for joining us today, and I'll hand over to Phil to introduce Jeremy, our presenter.
Thanks very much, Bianca. Good morning to you all. Thanks for coming along. We've been running these sessions for a little while now in person around the state. We ran 5 sessions. We nearly got through them all without anyone getting sick, but we got there in the end, which has been fantastic. And the feedback's been fantastic for people, and it's been nice to get out and about. So we're now offering the sessions as online versions, just to get it to people who couldn't make those other sessions and get this information out to you. I just want to acknowledge the support of Sustainability Victoria in this whole session. So please, certainly very appreciative of the support. And, it's a partnership that we've been running for quite a few years now, and it seems to be working pretty well in terms of getting some really good information out to you all there. The first speaker, the speaker I want to present this morning, sorry, this is the first session. There is a session running next week at the same time and the same place. So if you haven't registered and you want to do that, please do that, which focuses on design, on construction. This morning's session by Jeremy Spencer focuses on design training. And Jeremy Spencer is from Positive Footprints. He's a long-time registered builder, thermal assessor and director at the design company Positive Footprints. They're a multi-award winning sustainable design and construction company, and he's worked for the last 20 years to show that energy efficient, sustainable construction and high performance construction is a cost-effective option and can be a mainstream reality. I met Jeremy probably over 10 years ago now, and he was already building 7- and 8-star homes then. So it's certainly been a while there, and he certainly worked in this field for a long time. Most Positive Footprints homes are operationally net zero or close to it, using pretty much standard construction methods and commonplace technology. Jeremy's a lifelong educator, has lectured, presented, taught and advised builders, building designers and the public on how to build low impact, cost effective homes, which is a passion he continues. He sits on the board of Design Matters National and Builders Declare, and is a long-time judge of the Architecture and Design National Sustainability Award. So please welcome Jeremy Spencer this morning. Thanks, Jeremy.
All right, well, thanks everyone. This is a little bit different for me not having faces in front of me, so I'll be talking at my TV monitor here for the next 1.5 hours or so. I've got a cup of coffee, so I'm sort of sorted. I hope you guys are comfortable at your end. What I'm hoping to do today, this is all the design training module of moving from 6 stars to 7 stars and whole of home. So I'm wanting to give you the tools and the knowledge so that you can thrive, understand the new environment that's coming your way quite quickly, potentially in September, but also to thrive within it and to produce homes that are very low carbon impact. So what we're doing today is I'm really going through the whole entirety of the whole of home process, and not only letting you know how it works, but also giving you pointers and tips along the way to make sure that you can use it to produce homes that are as low impact and potentially carbon zero outcomes. So today we're just going to start looking at the background, where the building code is heading. I'm going to show you job that I put through the Sustainability Victoria Whole of Home tool. They're the first whole of home tool off the ranks, but each one, I believe, of the current NatHERS software will bring out their own version of the whole of home tool. But this will give you an idea of how it can work for you, how you can use it, what it's all about. So that's useful to show. Then I'm going to move into the meat of the presentation today, and that is following these 5 steps of following the whole of home process to produce a house that is a very, very efficient net zero home, potentially. And whole of home is really just about combining what is currently a thermal assessment, you can see there on the left, the 7 stars, with appliance efficiency and putting them together in the one package so that you assess the whole house in its entirety. And that way you can say, not only is this house thermally efficient, but you can then say, well, this house, how much is it? How much energy is it going to use overall? How much is it going to cost to run? So it's moving towards having a figure, a little bit like on a car, when you go buy a car and you see the sticker up in the corner of that says how fuel efficient the car is. That's sort of where we're moving to in the building industry. And the first part of that, the 7-star part of that, we'll be looking at passive solar design. NatHERS, the NatHERS software is really looking at how well does the house perform in its climate, or how much energy does it need to maintain a comfortable climate. And to build a house or design a house that is comfortable in its climate, passive solar design are the tools that you're going to need to know if you're involved in the design process. It's also basic information at this stage. Even if you're just building plans that come across your desk, you're going to want to know, when I look at these plans, say they're at preliminary stage, are they going to rate up to 7 stars? Do I see any issues that says to me, well, maybe I don't want to spend too much time as a builder costing this just yet until we get a thermal performance assessor to check it out. Step 2, moving on to using First Rate 5 or the other NatHERS tools as design tools rather than compliance tools. So I'm going to talk about that. Then we'll move on to the whole of home part, which is including appliances and looking at each one of those appliances there on the right, and what choices you might want to make if you want to choose more efficient versions of those. The last step, of course, to producing a net zero home is to include photovoltaics on the roof and potentially car charging. That's coming in the future, so I'll mention that. And lastly, of course, as we move into high performance, that does impose a bit of risk on builders and designers and thermal performance assessors as we're promising more. So I'm going to talk a little bit about as-built verification and what can be achieved. So a lot to get through. Let's get into it. Background and Sustainability Victoria Whole of Home tool. So this is basically why we're here. This is the graph of the carbon dioxide emissions for the world over time. And you can see it's growing. We're now at 36 billion tonnes and it's still shooting upwards there. And it was this graph that, and the associated climate change that's causing that led to leaders all around the world committing to net zero by 2050, our government being one of those. And what that means is that every industry in those countries are going to have to wean themselves off a fossil fuel, some call it an addiction, but a fossil fuel way of producing what they do, to a low carbon or a net zero carbon way of producing their product. And if you look over on the right, of that 36 billion tonnes of carbon dioxide currently being produced, 39% of that is related to building and construction industry, either in the operational energy use of our buildings or the carbon that goes into, or the energy that goes into the production of those materials and the associated carbon. So that's, it's a huge amount, 39%. And if we're wanting to flatten this curve, the onus really is on the building industry, rolling up their sleeves, getting on with it. Don't be discouraged though, because we have so much technology now, we can really make a big impact on that. And that's what I'll be showing you today, at least in the area of homes. It also means, of course, if you're in the building construction industry, you have a big chance to make an impact and a real contribution to a better future. Now, if we bring it back just to homes, what you're looking at now is the pie graph of the average Victorian home. I'm just talking about Victoria today when I'm talking about all the passive solar design principles, primarily looking at Victoria. And this pie graph is what you get if you average all the new homes and existing homes across Victoria, you average them all together, you look at where they're using their energy, this is what you get. Most of it goes onto space conditioning, you've got that big 60% wedge, and most of that space conditioning is going on heating. Most of the year we're trying to heat our homes to get to a comfortable temperature. Maybe 20% of that is cooling when it gets into the summer period. Water heating, also very big. Lighting and cooking, pretty small. And then there's just general appliance use. Now, in providing all those services in that pie, if you look over on the left, you can see that the average Victorian home, second point down, uses or creates 8 tons of carbon dioxide every year in burning fossil fuels, either coal for the electricity or gas, burning fossil fuels to meet the wedges or the what's going on in the wedges of that pie. 8 tons of carbon dioxide at the moment are released, and we have the dubious distinction of being the most carbon intense housing in Australia, primarily because of our brown coal. To put that in some sort of perspective for you, and a fun little fact is Australia has some of the biggest homes in the world, 230 square meters or so. And just so happens that if you took all the air out of the average new home, 2.7 ceiling heights, and you replace that air with carbon dioxide, that house would hold about a ton of carbon dioxide, if you think of how big is a ton of carbon dioxide. So effectively, each year, the average home is releasing 8 house-sized balloons into the atmosphere full of carbon dioxide each year. Good news, of course, is I'll be showing you today how we can get rid of pretty much all of that. The other thing I'll be using this pie graph for is to show you how the strategies that I'm suggesting today, working with the whole of home methodology, how the strategy that I'm suggesting affect that pie, that average pie, so you can see what makes sense and what is useful and how it contributes to reducing the energy we use. The other good news is that the building industry already has actually a roadmap of how the building industry is going to move to a net zero industry, or at least the start of that. It's called the Trajectory for Low Energy Buildings. This was a document that came into existence back in 2019 when the then energy ministers in each state got together under COAG and signed this document off. It's quite an ambitious document. And it's worth a read. It's only a short document, but if you read that, you'll understand completely why we've got the proposal that we've got into the 2022 NCC. This document is the guide that the Australian Building Code Board is following. So that's their roadmap. And this is the schematic of that roadmap. And it has a number of iterations over until 2030. Commercial buildings above the line, residential buildings under the line. I won't go into each one of what's going to happen in each one of these years. But what I will do is I'll just want to read out for you, especially for those with small screens, where this is all heading and by 2030. And 2030 is not very far away. I'll just look around my screen here to be able to read the edge. So I'm just going to move my thing a little bit. Says zero energy and carbon ready buildings. So this is the definition. This is where the Australian Buildings Code Board is trying to take the building industry by 2030. And this is the definition. A zero energy and carbon ready building has an energy efficient thermal shell and appliances, has sufficiently low energy use and has a relevant setup so that they are ready to achieve net zero energy and carbon usage if they are combined with renewable or decarbonised energy systems on site or off site. So effectively it's a building with a efficient thermal shell, efficient appliances inside, such that if you put photovoltaics on the roof or some other renewable energy source, that building could produce as much power over the year as it draws in. So it's net zero. The other thing I want to just point out is what's happening in 2022 for residential. Let's have a little read of this. It says to introduce an energy and carbon usage budget for residential buildings that includes appliances already covered in the NCC, which is hot water, pool pumps and lighting, adds a new requirement for space conditioning, increases thermal energy efficiency requirements, and allows for additional energy performance through on-site renewable energy. And if that sounds familiar, that is because that's exactly what the proposal is. We'll see exactly what gets through in September, but this is the proposal at the moment. And it is, first of all, on the right here, you can see it is to increase the thermal performance of the building from 6 stars to 7 stars. First major increase in a decade or over a decade. And then also to add on whole of home. And whole of home is these major appliances getting added into the calculation. And the way that's going to work, that's heating and cooling, lighting, pool pumps, hot water, and on-site generation. And the way it's going to work is this. When you do a thermal performance assessment, when you do a rating, you will, first of all, have to get the house to 7 stars. That's a baseline. You can't go lower than that. You have to get to 7 now. And you also have to show on your plans that you're putting in appliances that meet an average level. They're calling it a benchmark appliance. So in each one of these categories, there will be a benchmark appliance. It's not energy generation, that's a little bit separate. But in the other 4, there's sort of a benchmark level. And if you put in a heating and cooling appliance, if everything is above the benchmark and you're above 7 stars, you pass. The other way you can pass, you can do a little bit of a trade-off amongst these appliances, and you can have say a heating and cooling appliance that's below the benchmark, but your hot water might be above the benchmark. And when they do the calculations, the house as a whole is above the average benchmark home. The other thing that could happen is you could have all of your appliances below the benchmark, but put on enough photovoltaics on the roof to lift the house above the average energy use of this benchmark home. So that's the proposal that's coming our way. What that will mean, of course, is that you're going to have a bit of information. If you're a designer, you're listening to this, you're going to have to start putting information on your plans about what appliances you're going to put into it. And I'll show you some of the choices as we go through this. So this is the First Rate 5 Whole of Home Pilot Tool website portal. And I've put one of my projects through it. And so what you do is you do a normal thermal performance assessment on the shell as per normal using First Rate 5 software in this case, and then upload it to the tool, the Whole of Home tool. And then you're met with some pages, and here you get to put in your appliances that you put into the home. So in my case, in this house, we had reverse cycle air conditioning throughout for heating and cooling. It did both. And you just put in the number of stars. The tool is quite useful in that it just tells you what information it requires. It doesn't take particularly long to find that information and put it in. I think it'll be maybe 15 minutes to run this whole simulation. The next page, after you put in heating and cooling, and later on I'll show you some of the options that you get to choose from. But this is for this particular home that I did. This is what we had. The next page has cooking. This was an all-electric home, so we had an induction cooktop and electric oven. But I do want to point out that under the 2022 proposals in the NCC, cooking is not part of the whole of home system. However, under the trajectory for low energy buildings, they do talk about adding other modules later. So my guess is later cooking might be added. At the moment, pool pumps is in there, but not pool heating. So pool heating might be added at a later stage, and maybe even car charging down the track. Water heating, we had a heat pump water heating. Like I said, it was an all electric home. It was a high efficiency version. So we're putting in good appliances here. Now, under the plug-in appliances and lighting, you get to put in what your lighting is, either 3, 4, or 5 watts per square meter. So again, if you're a designer, you might want to start, if you're not already doing a lighting schedule, so that you can show with your LEDs your 3 watts per square meter, and you pick up a few points in here. If you're a thermal performance assessor, I think what will happen if you don't have that information for you, you'll just default to worst case scenario, which is 5 watts per square meter under the construction code at the moment. Plug-in appliances, you don't have to interact with or muck around with, you know, TVs, fridges, anything that plugs in. What happens is the tool just puts in an average amount for the average home into that space for you. Is there a pool? There wasn't a pool in our project, so we click no. If you click yes, you get to put in what pool pump type. And again, I'll show you that a bit later. We did have solar panels on this house. This was a 7.2 star home. It had a gable roof facing east and west. So we put on 6.3 kilowatts of panels, some facing east and some facing west, about half and half split. We had no batteries, so click no there. All right, so that's all the information that you have to add. Again, it doesn't take very long, especially if that was already on the plans. Then you press calculate. It simulates a year of operation and using the house. And it comes up with information a little bit like this. And you can see along the bottom, if we look along that graph along the bottom, that's each month of the year, gives a monthly profile. There are 2 column graphs on each month. The dark green there is the electricity being produced by the photovoltaics on the roof. The coloured column graphs are the energy being used by the house in the various areas of the home. And you can straight away see that in all the hotter months of the year, we're producing more energy than the house uses, and then we use a bit more during winter, but on average, producing more power than the house is using over the year. And up in the top left-hand corner here, you can see a summary of that. So this house draws from the grid electricity, and that electricity requires coal to be burnt and 3.99 tonnes of carbon dioxide to be created. However, it's producing more power than it uses over the year, and though that renewable energy, those green electrons, if you like, are flowing out of the house into the grid, neighbours are using them, and that offsets the need for them to draw on fossil fuel-based electricity to the tune of 7.27 tonnes offset, to give a net emissions profile of -3 tonnes of carbon dioxide. So effectively, this house, instead of putting up 8 balloons of house-sized balloons of carbon dioxide, it's drawing in 3 every year and folding them up and putting them into the cupboard. So the grid is a bit better off, if you like, with this home on it. The tool also splits where the energy is being used in the house, and it splits it by energy use, by emissions for the different things that's going on in the home, and also by the cost to run those areas of the home. And so what I can see, this is my sort of feedback on using the tool. I'm really quite excited about the tool. It will answer a few questions. First of all, it will answer for homeowners and for builders and designers, how much photovoltaics would I need to put on the roof of this particular home for it to break even? And a lot of clients want to know that. That's one question. Also, potentially for the savvy builder or designer or developer, you could do point of sale upsells on appliances. So I had exactly this situation this week, in fact, where a client was asking me about the difference between an efficient heat pump hot water system versus an instantaneous one, because they like the fact the instantaneous use less space, which they do. That's their good point. So we ran it through the tool. What we found was there was a $400 difference in running cost over the year of going from the instantaneous to the heat pump was $400 less per year to run. Also, the instantaneous produced over 2 tonnes of carbon dioxide a year. So there was a big saving, of like a 4-fold saving in the amount of carbon that goes up in the atmosphere by going to the heat pump version. So you can also run different, you can put in double glazing and single glazing and run 2 different jobs through, and you could see what the difference was there as well. So very, very useful. And lastly, it makes energy efficiency visible in a way it wasn't before. We've had stars for a long time, but that doesn't actually tell you how much the house takes to cost to run and what the overall emissions are. This starts to get to that. And so potentially it could be a marketing strategy. In a way, the same way that sticker on the cars is something that you look at when you go and buy a car, similarly. All right. So that's the tool, that's the background. Let's get into how to actually work with the tool to achieve a very low energy and net zero outcome, or net zero ready, as I say here. Net zero ready is simply, it doesn't have the photovoltaics on the roof yet, but it's ready to become net zero if you did put them on. All right, so step one is using passive solar design to achieve 7-star plus performance. Passive solar design, as I said, it's just designing for climate and to be comfortable in the climate. In Victoria, most of the time, we're trying to heat our homes, as I mentioned. So if we can get the sun to come in our homes in winter, we'll get some free heating there and lower our energy use in the home. Likewise, in summer, on the afternoons in summer, especially around Melbourne, often get sea breezes. You get evening breezes in a lot of places throughout Victoria. If we can design a breeze path to pick up that, again, we get a little bit of free cooling, which lowers your, raises your NatHERS score a little bit. If you can lock to the mass of the earth, you know, you can get, that'll give you much more stable temperatures inside. The outdoor temperature can be going up and down, fluctuating, but if you're locked to the mass of the earth, your internal temperature will be much more stable. So I sort of look at this a little bit like a solar hot water heater. You're still going to be putting on space conditioning, mechanical heating and cooling, but in the first instance, you've minimized, by using the natural resources, you've provided most of the heating and cooling in the home, and that mechanical services are really just an extra booster, if you like on solar hot water, you get that the booster on the back if it's not quite the right temperature. That's the sort of idea here. Now, before I tell you the rules that you'll need to know and understand when you're looking at plans, I just want to show you how the star rating system affects this space conditioning wedge, which is what the thermal performance is all about. So currently we're at 6 stars. If you designed to 6 stars and you built to 6 stars, which is not always the same thing, as we know. In fact, you'll learn that from if you go to next week's webinar with Sean from ATMA. He'll tell you all about problems that you can have in standard construction and how to address those. However, if you do design and build to 6 stars, compared to the average home, which includes a lot of existing homes, that's the sort of saving that you get on that pie. So significant, that's why we were doing it. If you go to 7 stars, that's more like about 1/3 of the pie is saved. If you get to 8 stars, higher again, 9 stars and 10 stars. So in Victoria, because our space conditioning wedge is so big, design does play a big part and is really an important thing to work on if you want to get a good outcome. However, we don't need to go to 10 stars. 7 stars is plenty to get to a net zero outcome, as you'll see as we progress. All right, let's get into the secrets to 7, 8, 9, and 10 stars.
Sorry, Jeremy, just before you jump in there.
Yep.
Just got a couple of questions that might be relevant.
Okay.
The lighting standard, that's at 4 watts now for housing, or we think?
The lighting standard is, yeah, it depends on outdoor or indoor. I can't remember exactly, but I'm pretty sure it was at 5 watts in
5, yeah.
Yeah. I'm pretty sure 5 watts is the standard. Yeah.
Yeah, look, I'm not sure if that's changing. That might be one of the details we'll need to see when it actually comes out. Do you know that?
I'm sure there's a lot of designers yelling at their screens at the moment. Sorry, I control the construction side of Positive Footprints. I'm not doing the design part. I'm not 100% over everything.
I have a feeling it might change to 4, but I'm not sure. But we'll have to wait and see in October when it comes out.
Yeah.
And there's no provision to include batteries at the moment, is there?
You can put them in the tool, but no, there's no, under the NCC, it doesn't talk about batteries at the moment. Yeah, but you can at the moment, you can put them into the Sustainability Victoria tool and see what benefit or otherwise they may have. So yeah, it's a useful tool for giving you feedback from that point of view.
All right, thank you.
All right, so let's get into these are the rules, or I like to think of them as the tools in the tool belt. At the moment, the building industry, when we went from 5 stars to 6 stars, nothing really had to change too much with the design side of things. You could do almost exactly the same thing and just get to 6 stars by increasing insulation to as much as the cavities could hold. And then if it didn't get to 6 stars, you would then start to put on, double glaze the home, and it will get to 6 stars, and the thermal performance assessor would stamp it and give it back. Most of the time, that strategy will probably still work. I'd say in most of Australia, 90, 95% or higher time, that strategy can still work. But I don't think that's the most cost-effective way of achieving the 7-star outcome. And I also want to just point out that with 7 stars, you got to remember this is 7 out of 10. So it doesn't, 7 out of 10 is like a B on a test. So we just need to hit these rules somewhat. We don't have to hit them 100% every single rule. There's a bit of flexibility is what I'm trying to say with the 7-star standard. So there's still plenty of opportunity to do lots of different designs and get it over the line. However, if you want to pick up some points under NatHERS, these are the things that you want to start to look at. And as I go through these rules, if when you're looking at your own designs or plans that come across your table, if you're thinking about these, there's 5 rules, 1 for each finger. And as you're thinking about these 5 rules, when you're looking at plans, if you think, oh, I didn't hit that one, that'd be red flags. And if you're starting to get 1 or 2 red flags, then it might be, oh, well, maybe we need to get a thermal performance assessor to have a look at this before we go too much further. Anyway, I'll talk about that in a minute or a bit later on. So first rule, sun rises in the east and sets in the west, but it doesn't go directly overhead because we're in the southern hemisphere. It goes on the north part of the sky down in Victoria, which means that if we put our living spaces and appropriate windows on that north side of the home, we can get free winter heating for nearly 12 hours a day during winter, which is when you need it. And also because the Earth is on a tilt as it goes around the sun, it's higher in the sky in summer, which means we can put out an eave on that north side of the home to keep the summer sun out of the home. So we're very lucky like that. Now I'm going to give you a quick rundown of the sort of the quintessential passive solar design layout. North is up the page here. There's no overshadowing, so it's sort of perfect conditions, but this is how I like to think about things, and then we'll discuss them. So first of all, I put on the sun path, and you notice the sun path here, we've got red and we've got blue going on. And that's because actually the sun doesn't always rise in the east, doesn't always rise in the west. In fact, it only does that on the equinoxes. In the summer, the days are much longer. It rises in the southeast down here and then goes all the way around, sets on the southwest. In winter, the days are shorter. It rises in the northeast and goes around, sets in the northwest. And we can use that with our layout, as you'll see. Sorry about that. The other thing that I always like to put on is the prevailing breeze. Now, this was this particular design I designed in Melbourne. Melbourne, we get a lovely sea breeze that comes in from the south in summer. It's the summer one that you want for potential cooling. So wherever your local summer breeze is, that's what you put on there. Then this is how I generally would do a layout. Living areas, put on the north. The reason we put the living areas on the north is that people can be in those living areas all day, and then they can be in those living areas well into the evening. And so we want to prioritize those. And NatHERS software assumes that people can be in there long hours and that we'll be wanting nice, comfortable temperatures well into the night. So we prioritize the living spaces by putting them on the north. I like open plan sort of living areas, makes a smaller home feel big. And you can see if we put the kitchen on this side, if we did have windows on the south of the kitchen, windows on the north, we could quite easily have that breeze blowing across our living space in summer where people are hanging out. So not a bad setup there. Kids' bedrooms, I put them at the back of the home, quite a standard sort of place to start to put them, a bit of security, but really I've also put them there. You can see in summer, the sun sets down here in the southwest. And the last thing you want in summer, when the sun's really low and getting under all of those horizontal leaves and things that you put out, you don't want that last oomph of sunlight coming into the living space. So you can see this kids' bedrooms is almost like a bit of a buffer from that summer sun there. Of course, you don't want those kids' bedrooms being uncomfortable at the end of the day in summer as well. So you wouldn't want your windows to be too big on that west side. And potentially you might want to put in a bit of shading from that summer setting sun. Of course, it doesn't block the winter sun. So a bit of landscaping is always quite useful. Master bedroom at the front of the house, just to split it away from the kids for a bit of privacy. Well, we could have put that on the south. There was a space, we put it on the north, because the more rooms that you can put on that north side of the home with windows onto them, the better the performance of the home is going to be. That left the space on the south for the garage. And once again, that garage has a similar use as the kids' bedrooms, but this time in summer in the morning. So what you don't want is your home heating up really early when the sun's rising in the southeast. So the later you can make the heat up of the home, the better. So the garage there is a bit of a buffer from that morning sun. And then there's a space there to put the utilities, the bathroom, the laundry and such on that side of the house. And you can see what we've done is sort of prioritize the living space, and all these other rooms I almost think of as extra insulation buffering around that living space. So it's got very stable temperatures. And here's the outcome of that particular floor plan there. You can see the living space, bedrooms, everything like I just showed. This one came to 8.1 stars. But this, I say that mainly just to point out the fact that this design is not perfect from a passive solar point of view by any means. You can see that this master bedroom area, when the sun rises in the winter, it actually gets in the way of the sun shining into that living space. In fact, it probably won't until the sun moves around, you know, into the mid-morning. My point here is that you don't have to be perfect. We could have gone straight across there, but we actually wanted to have a setback courtyard, so you have a bit of a better outdoor, you know, facility for that family who lives in that home. But this is what I ask myself, or what you should be asking yourself as well, is, are my living areas getting north sunlight most of the day in winter? And so it's really just the logic that I'm getting at here. With all of these rules, you don't need to know too much formulas and that sort of thing. There is one that I'm going to show you, but most of all, it's about just the logic of it. And I'm just trying to get sunlight into my living space most of the day in winter. And if you do, that will be a tick. If you can also answer this question, how many other rooms are getting northern sunlight in winter, and some of the other rooms are also getting northern sunlight, well, that's a big tick. And you can say, right, I've done this rule pretty well. If the answer to both of those was no, well, that would probably be a red flag. And you'd want to hit the other rules that I'm going to go over shortly. You know, you'd want to hit them well. This is the particular home in question. Two things to point out. One, it doesn't have to be this style. Style is independent of passive solar design, can be any style. Though I do want maybe to promote the idea of making a spot for photovoltaics. Photovoltaics are one of the technologies that makes the whole net zero, you know, thing that we're trying to achieve as humanity. It makes it possible in construction. And also with potentially car charging later on, photovoltaics are only going to become more useful in the home. So if you can make a spot for them to go, all the better. This just shows you the inside of that particular house. This is obviously shaded at the moment, but during the winter, when the screen's retracted, you get the sun streaming in here. The thermal mass can hold it. It's got good insulation and good quality windows, which we'll talk about too. Okay, another thing to think about when you're looking at designs that come across your desk, this is the elevation. So I always start by opening up plans. I look at floor plans and look at the layout, you know, are the north, are the living spaces on that north side? Great. Next thing I'll do is I'll look at elevations, and I'm wanting to see which elevation is likely to be north. And the one that has the most windows, ideally, is the one that's north. So in this case, this is the elevations of the design you just looked at. So you already know that, that this one up top is north. But you should be asking yourself when you're looking at your own plans or looking at plans come across your desk, can I work out which direction is north by looking at my elevations? And if you say to yourself, well, I reckon that one's north, but you find out that that's east or south, you know, that would be a red flag. Maybe send it to the thermal performance assessor or just query it with the designer there, if you're the builder looking at it. I put all the directions back in there. Yeah, so that's basically the question you just want to ask yourself there. So that's all about orientation. And it's as simple as, I know that was a perfect situation, by the way. There was no overshadowing. And, you know, if there is a neighbour on the north, well, maybe you've got to go double story to get that sunlight coming in if you want those 3 points. I should also just point out that with that particular design, I did a couple of things. I tried rotating it east and west, because some people were worried, well, what if I don't have a good block? What if it's got a bad outlook? If I rotate that design set of 8.1, it goes down to 7.7, 7.6 if I rotate it east and west. If I rotate it the whole way around, more like 7.5, around about a half a star decrease. And that's because I didn't go overboard with windows, which we're going to talk about right now. The other thing that I also modeled was, what if it's facing north, but we've got a 4-story neighbor all the way along the boundary line? Worst case scenario. Then it went down to 7.2. So my point there is that orientation is great. You can pick up some fantastic points, but it's not a killer. You know. All right. Rule number 2. So we've orientated our floor plans, tried to pick up northern sunlight, and it might mean that you move the living space around. If there's shading at the front of the block, then living space goes to the north. If there's, you know, overshadowing at the back of the block, living space might go to the front or upstairs. You know, you've done what you can to try and get some northern sunlight into the living space most of the days in winter. That's a tick. You're on your way to getting into that 7-star band quite easily. Now, the next part is how much windows to put on and where do I put them, and how do I design an eave to keep out the sun in summer. So window consideration is crucial to performance. I used to do literally thousands of energy ratings as I was getting this company going for people. And what kills designs is having too much windows and having them in the wrong spot. As it says here in this little bubble, once you've insulated a home, this is up to 40% of a home's heating energy can be lost through windows on average, and up to 80% of its heat is gained through windows. So windows are really important. And to also put it into a little bit of perspective on how important it is to not overglaze. Windows are great during the day if sunlight's coming in, but they're not great at nighttime, typically during most of winter. They're just losing heat for you. And if we look at this wall, so you understand how much heat they lose. If you look at this wall, this is a 90mm stud wall, and it's in the stud work, we've got R2.5 bats. Actually, might be R2.7 in this one. We've got a permeable reflective foil on the outside facing onto an air gap. Maybe that's another half an R rating. And then if you include the plaster and the, I think this was Ecoply on the outside, I've got about an R3.5 of insulation across the wall. Now, if these windows were single glazed aluminium and we converted their U values to R values, they would have an R value of around about 0.2 or so. So that's 0.2, R0.2 versus R3.5. So it's about 40 times worse or so. Now, these windows, in fact, are double glazed, argon filled, low E coated, timber windows. They're pretty high performance. Even with high performance, they get to an R rating of about 0.5 versus R3.5. So they're still losing and gaining heat 7 times faster than the walls next to them. All right, so it leads to the question, well, where should we be placing our windows and how much window should we be putting in? These are 2 interesting graphs for you to look at. This one is in winter, and what it is, it's a house with walls facing different directions with no eaves and a 1 square meter window in each face. And it's just looking at how much energy comes into that window versus how much gets lost over a 24-hour period. This is single glazing. And you've got a dotted line here going through it. And it says single glazing, heat gain is greater than heat loss above this line, and heat gain is less than heat loss below this line. And this is how much heat is coming in. So you can see it's only on the north, the northwest, and the northeast that if you had single glazing, only those directions will you be gaining more energy through your single glazing than you're losing. Any other direction, you're going to be losing more energy over a 24-hour period. And thermally, those windows aren't going to be doing good things for the home. But there's also a green band that runs through this, and it says heat loss range for high performance windows. So if you do start double glazing, you know, PVC windows, thermally broken aluminium, better frames, low E coatings, argon filling, if you improve the performance of those windows, you may very well find that, well, maybe the west window is also a net benefit for you, as is the east as well. So interesting little graph there. On the right here, we have the same setup, the same house, no eaves, but this time in summer. And this time the dotted line represents a 2-bar radiator operating 3 hours a day, which is what you don't want your windows to be in summer. Heat will come in your windows, but the less the better. And you can see that the best performance in summer is actually from the south, because the sun doesn't shine too much into the south. But interestingly, the next best is north, or almost the next best. Southeast is also good. Next best is north. And you might ask yourself, well, that's a little bit counterintuitive, because we've just been talking about putting our windows on the north. So, and then the sun's always on that north side of the house. Why is north the next best direction? This is without eaves. And the answer is that in summer, the sun is very high in the sky. And when the sun is high in the sky, it's actually shining down on the window. And it's like, if there's my window, I don't know if you can see that, but it's hitting it at an acute angle, and a lot of that sun gets reflected off. A lot of that energy gets reflected off and doesn't go through. So north windows are pretty amazing. East and west are not great there, because when the sun's rising, it's hitting those east windows straight on, and when it's setting, same thing. It's hitting those windows straight on. Most of that energy is going through when you don't want it. So that leads to these rules down here. First rule is to prioritize north. No surprise. How much should you go? Well, because the sun isn't there at night time, you don't want to overglaze on the north, because this house can only hold so much energy. And so the rule of thumb, these are rules of thumb. You can vary from them, but keep them in mind if you're involved in the design. You shouldn't go over this 25% floor area. And what I mean by that is, if you've got, say, a living space that's 100 square meters, you could have 25%, 25 square meters of north window in that room would probably be okay. If you're over that, you're probably starting to overglaze and you'll be losing too much energy at night time. After north, east is better than west, because we're in a climate we're trying to heat most of the time. If we can get our homes heating early, then it's a benefit for the house over the day. So even though you get the same amount of sunshine on east and west, east is the better direction. And you can go up to 15% floor area there as a rule of thumb. On the west, you're really just trying to go for minimum window sizes as per the daylighting requirements in the code, which is 10%. And the same on the south, because you're just going to be losing heat typically over the year to the south. So when I'm thinking west and south, I'm typically, or when we're thinking about design in the office, we're mainly looking at where I can pick up breezes for breeze paths, and where there are views that you want to frame when I'm thinking about those windows. Now, if all those percentages get a little bit hard, I don't actually use that when I'm looking at other people's plans that come across. I'm doing some sort of consultation. What I will do is a simpler one. I'll simply add up the total floor area of the whole thing, and I'll say to myself, is the window to floor area, and I'll add up all the amount of square meters of window, is the window to floor area less than 25%? And then, are most of the windows on that north side of the home? Is the highest proportion of windows on that north side of the home? If yes, then tick, this house is probably going to do pretty well. Now, you can push those areas a bit. If you start to have high performance windows and mass, you can maybe push up to 30%. We'll talk about thermal mass shortly. Now, so now you've got, you have an idea of how much windows, where they should go. But if you're putting them on the north, you also have to think about, I don't want to put them into shade on the north. You can have shade on the north side of your home. You could have other houses that are close by that are shading that north side. Like in this situation, instead of having a floor to ceiling window, you might want to raise the sill so it's out of the shade. If you have an articulated face, even though it's facing north, you're going to get a bit of shade on those windows. You're trying, because the window is the weakest element of the thermal skin of the home, just try and get into the sunlight. That's the main point of this particular slide. All right, so we put most of our windows on the north. How do we shade the windows in summer? Even though north windows are still pretty good in summer without eaves, they become even better with eaves. So you definitely want to put them on. There is a simple rule that works really well for Victoria. It's called the 45% rule. And this is a rule of how to design an eave that will let in the winter sun, which is lower in the sky in winter, but keep out the summer sun, which is higher in the sky. It works for the north, doesn't work for east and west because the sun is rising and very low in the sky when it's rising and very low in the sky when it's setting, and will come in under any eaves. East and west, you either want to minimize windows, put in some plantings, have some vertical shading, something like that. But for north, we can design an eave that will just sit there and do the job. And this is how the 45% rule works. You measure the distance from the sill of the window to the underside of the eave. And whatever that distance is, your eave should stick out 45% of that distance. And that includes to the furthest shading point, which is usually the gutter. So for instance, if that height there was 2 meters, 45% of that, 900 millimeters. And maybe my eave is 150 mil eave. Gutter. My gutter is 150 mil gutter. That leaves an eave, the actual eave part, 750 mil. So I'd be having 750 mil eave sheets there, or cutting down to that. Now, the other part of that, you'll see in winter, if we ran our window all the way up to the underside of the eave completely, there would be this spot at the top of the window that's always in shade and not performing for us. So ideally, you want to pull the window head down, and you want to pull it down by about 1/3 of that eave. So I just think 1/3, if that was 900 millimeters, I'd want to pull that down around about 300 millimeters. So that's how you design up the perfect eave on north. Just remember, the sun is not always directly in front of the window. So if you are just putting eaves over windows individually, just run them past on either side by whatever the depth you worked out for the eave, just run it past the same amount, and that'll do the job. And then I like to think, when I'm looking at plans, I like to imagine that I am the sun. And obviously, if you're a designer, you can model these things in your software, but it works really well. It works really well. Just imagine, is that, sorry, there's a beep. By the way, Phil, if you are listening to this and want to ask questions anytime, just I've minimized your hand, so just yell out instead. All right, sorry everyone.
Well, look, if you've stopped there just for a sec, I've just got a quick one. Is there any gain in insulating the internal walls?
Yep, that's the very next point I'm going to look at.
Okay,
great. That's the third rule is insulation. So once we finish windows, we'll be looking at insulation. Yep. All right. So this is just a really easy way. If you pick up a set of plans, you can imagine that you are the sun. So in winter, the sun rises from the east-ish, sets in the west-ish, and gets to a height of about 30 degrees on the sky. So I'm imagining, when I'm looking at my plan, sort of imagine myself starting low, going up over, and then going down. Can I shine in under all the eaves that are there and get into the home? Can I see into most of the home? Then I do the same thing for summer. Okay, now I'm at 78 degrees or so for Melbourne, and now I'm going much higher in the sky, and I'm looking down on my plans, and are the eaves actually stopping me seeing in? So you can just sort of imagine yourself as the sun. All right, so assuming you've used the 45% rule and designed up your eaves well, the next thing to think about is the performance of the windows that you're actually putting in. They're most on the north, yes, and then the east and the west and the south, but still, they're the weakest element, and the higher the performance that you can achieve for your price budget, the better your house will perform, and it makes a significant impact to the windows, possibly the biggest impact of them all. So what do you need to know? This is what you need to know when you're designing or you're choosing windows. There's 3 different numbers, if you like, that you need to know on windows. There's the U value, the solar heat gain coefficient, and air leakage. Now, the most important of those are U values. So I'm going to start with that. U value is just a measure of how well a window conducts. So with windows, instead of talking about resistance and R values, they're talking about the opposite, which is U values. Now, you don't want a good U value. You actually want a window that resists heat flow and keeps the temperature inside the home and doesn't let it out in winter and doesn't gain heat in summer. And when we're talking U values, you do need to be aware that there's U values, this UW, which is a whole of window U value. Most documentation you pick up will be talking about the whole of window, and that's what you want. But sometimes you might pick up a U value, it's just talking about the glass, the U value of the glass, or the U value of the frame, or if it's double glazing, there'll be a U value of the spacer. All those things get added together to become a U value for the window. So just make sure that you're choosing, you're looking at the right data there. The other thing to be aware of is that if you're looking at overseas windows, they'll have different U values than they do here because they use different protocols. And if you're in America, for instance, they'll be using imperial measures and all sorts of things. So you can't really compare one-to-one. With U values, the lower, the better. And if we look over here on this table, indicative U values for a variety of windows, you've got an aluminium window, single glazed aluminium window that has a U value of 6.7 and down to a U value of 2 for a double glazed argon filled, low E coated timber window, pretty high performance window. And what the U value actually is, if I have 1 square meter of window, and I have 1 degree of temperature difference on either side. So there's my window, I've got 1 degree temperature difference on either side. If I've got a U value of 6.7, what that means is I've got 6.7 watts of heat flow going from that side of the window to the other side of the window. If I've got a U value of 2, it means I've only got 2 watts of heat flow. So effectively, a U value of 2 is losing heat, more than 3 times slower than a U value of 6.7. So that is, that is significant. And if you want to think about it in R value terms, if you look over here on the left, an R value is just a U value turned upside down. Put a 1 over the U value, you get the R value. So 1 over 2, you get an R value of 0.5. 1 over 6.7, you get an R value of 0.1 there. Now, the other number to know about is solar heat gain coefficient. And the solar heat gain coefficient is simply a number between 0 and 1 that says how much sunlight gets through. So 1 would be 100% of sunlight gets through, 0, none gets through. And for assuming you have shaded out in summer, then we're just wanting to get as much sunlight as we can in winter to heat our homes in most of Victoria. Maybe when you're getting right up on the border, if you've got east and west facing windows, you might want to start cutting down the solar heat gain coefficient by putting on, low darkening shades, say on the window. You would confirm that with a thermal performance assessor. But for most of Victoria, you're really just wanting the highest solar heat gain coefficient that you can. And a good number for a solar heat gain coefficient, because the solar heat gain coefficient includes the frame of the window, includes reflected light that gets off and some gets absorbed by the glass. Around about 40% or 0.4 is a pretty good number for a high performance window. For single glazing, that goes up to around about 0.7 or so. Okay, now that you've got that information, how do you actually choose windows? Well, there's a fantastic resource for the industry called the Windows Energy Rating Scheme. And all of our windows have to get rated under that. On the last screen, you might have seen AFRC, Australian Fenestration Rating Council, or certification, one of those. They all have to be rated under the same protocol, and all of the windows that do get rated go to this Windows Energy Rating Scheme.net database. And so every now and again, I like to go to this database and just see who's making good windows. And you don't necessarily, the U value covers the performance. You don't need to think about, is it double glazed, single glazed, low E coated, argon filled? Those things all add into the U value number. So really you just can judge things just on U value. So I like to put in a U value here. I like, 2.5 or so, but anything under 3 is pretty good. And solar heat gain coefficient down there, I put as 0.4. And then you just search the database. You can choose what type of window if you want, what type of opening. We like casement windows. So I put that into the database, press sort, and you'll come up with a big list. This list actually goes down to 98 items in Victoria, that casement windows that satisfy my criteria. Then once you're on this page of the website, I do three things. First of all, I rank by U values. You click on this, it just ranks them by the U value. I then go down the list and I choose one that's got a nice high solar heat gain coefficient. Most of these are pretty good. And the last thing I look at is air leakage. So air leakage is in litres per second, of how many litres per second leak in through the seals on this window. So the lower, the better on that. And once I find a window that, you know, satisfies all the numbers, most of these are pretty good, I then go across and I see who's making those windows. And then you can go to those windows manufacturers, you can send them off some window schedules, you can get some ideas of their price points and what they have to offer. And then, you know, you can choose ones that fit in with your price budget and perform the best that you can for the price budget of the house. So very useful resource. All right, so a lot in rule number 2. That's probably the rule, the most intense information rule. But now you know where to put windows, approximately what size of windows to put where, and how to choose good performance windows and how to shade out on the north side of the home. So you'll be well on track if you incorporate some of those rules into your design. You'll be well on track to getting 7 stars and above. All right, third rule is keeping the heat in and out, and that is insulation. So what you want with insulation is, as you can see on this picture, you want a complete insulation layer all the way around the house. You don't want to have, you know, gaps in it, ideally. And you want to think thermal shell. And one thing I want to point out is garages, you should consider those. If you're not already considering those as external spaces, you should, because while they're included in the NatHERS rating, NatHERS assumes a lot of air leakage is going to be coming through garage doors, which is pretty normal. And often garage doors are, you know, they might be 1 mil steel. They're very conductive. So garages get pretty cold. So my advice would be to run whatever insulation you run on the external walls, just run it round on the internal walls. And don't be silly like I did here and put a sliding door going into a garage. They're very, very hard to actually seal. Casement doors going back onto a bulb seal, much better. Swinging doors. Now, this gets to Phil's question before. Should we do internal insulation? The answer is yes. And the reason is the NatHERS software zones off the home, and it assumes that, you know, laundry, WC and pantry don't necessarily need to be as warm as the living spaces, so you can zone the home. So some insulation between the utility areas, being pantry, laundry, ensuite, those sorts of areas, they should have insulation around them. You'll get a bit of a lift in the tool, and not only that, your heating and cooling requirements for your home will go down.
Jeremy, I've got a couple of questions, might be worth having a look at.
Okay, let's go for those.
Triple glazing.
Triple glazing, yes. Well, triple glazing is good, and you'll get a lower U value. So if you can afford it, go for it. But once again, it's the U value that you want to look at. And you might find that if you have a double glazed window with some fancy low E coatings and a nice argon or krypton fill, it might actually have a better performance than just triple glazing that has none of those extra coatings on it. So it's the U value is the number that you're after there. And
it's not going to affect the amount of heat being brought in through via the sun.
It does a little bit, yeah. It will a little bit, but of the two, the more important is the U value. So U value is first because that works 24 hours a day. The solar heat gain is better during the day. In the ideal world, you would have a window that becomes really high U at nighttime and really high solar heat gain during the day. But of the two, always go for the U value in priority.
Yeah, look, I know of, you know, there's a couple of houses I've seen with triple glazing and very cold areas. So some of the areas around Ballarat and places like that, I know you've gone for the triple glazing. Yeah. Can heavy curtains or block out blinds be added to the U value of the windows?
So unfortunately, under NatHERS, they assume for rating mode that all these homes get rated on, they just assume a pull down blind and like a roller blind. That's what they assume. And even though if you put on pelmets and you put on you know, good drapes and things, they have a big effect on the windows as long as they are used by the clients. But way back when, the NatHERS system, they assumed that they are just fashion items that come and go over the life of the home, and so they didn't include them in the rating. But I always let clients know that curtains are important, and so try and get them to invest in curtains.
And you know, how much advice on solar heat gain coefficient or tinting should be influenced by the client preference? For example, I'm more comfortable being cooler, so grey tinting, low solar heat gain in pick.
So later on, because we're talking about whole of home now, and later on I'm going to be suggesting you might think about reverse cycle air conditioning and PV. Now, if you do go and the all electric home route, those you'll be making heaps of power in summer, and you can just run your air conditioner. So I know that's sort of an easy answer, but it's true with the technology that we have these days. Overheating, unless there's a power failure, overheating won't be won't be as much of an issue. Of course, you should always try and work with your client's preferences, and as long as you're not right on the border of 7 stars, if you're 7.5 stars, well, you know, the client says, you know, I want this house to be better in summer because I hate getting hot in summer. I'm one of these people who don't like it. So then, you know, you might shade those windows down a little bit, and it might drop down to 7.2 or something like that. As long as you've got a bit of a buffer, you can then work to your client's preferences there.
Yeah, of course, and of course you're always working with views and what have you as well.
Yeah.
So
Correct.
You might know, or I think Grady's online, so he might be able to answer this as well. Everyone's time poor. Do any of the NatHERS approved software allow for the integration of Revit files or, you know, other sort of files to help with this initial assessment?
I wish. I've been wishing for 10 years that this was all just part of a CAD package and you got real-time feedback as you designed. That would be great.
Yeah.
I know that some of those tools have their own energy performance software, but they're not NatHERS accredited tools at the moment.
And there's a question about the same principles applicable for apartments.
Yes, is the answer. Yeah. When if you are interested in apartments, you should definitely watch the second construction one, where apartments can have problems with condensation being a smaller space, and that is all covered in the next construction webinar.
Yeah, and the practices make them generally more airtight as well. So correct, yeah, absolutely. Yeah. And issues of thermal bridging, which we will touch on in the next session, the session next week. Yep, absolutely. Thanks, Jeremy. We'll keep going. Hey?
Yeah. All right. So there's 3 layers with insulation. I won't go too much into insulation because it will be covered next week, and what can go wrong and what to do about it. However, there are 3 layers that you want to think about when you're designing a home. And the first one is the wrap layer. And really what you're trying to do is create still air space in the cavity. In standard construction, you're going to be putting bats in there, and you want to try and have as little airflow through those bats as possible, because they only work really well if they're in a still air space. The first bulwark against that is the wrap layer, and those are the rules. Simply correct wrap type, and Sean will talk all about correct wrap types, but you'd be wanting to use at least a class, well, I'd be going for a class 4 breathability, permeability membrane for that. And whatever wrap you choose, make sure you choose the correct tape that goes with it. And I'd be specifying that on the plans because you don't just want your, the tradie on site to send his apprentice down to Bunnings to get some tape, and they get whatever they get, and then it peels off in the cavity 6 months later and the house doesn't perform particularly well. And you should be taping to all penetrations and so forth. So the question I just asked myself is, have I specified wrap and tape on the plans, and have I detailed penetration? So this is the other thing. Don't leave it up to builders. It's hard for a builder to know exactly how, with windows, and to work out how I'm going to do the flashings, how I'm going to make sure water doesn't get in, and how I'm going to tape to windows, depending on my cladding types and things. There's a lot going on windows. So do the builder a favor, if you're a designer listening to this, and put on a little detail of how this all works together. But it does make a big difference. Bradford did some testing a few years back, and so they clad a big room and then sucked air out of it to induce 50 pascals of pressure, which is the same as a 30 kilometre an hour wind speed blowing over the home, to see how much air infiltration gets in and what some different strategies, how different strategies can affect that. And they found if you just put on wrap but no tape, you don't tape anything, you just put the wrap up, you get a 20% reduction in airflow through the wall. If you overlap and you tape all overlaps and you tape the penetration, so you tape the wrap to the window in this case, and they had a couple of windows, you get a 58% reduction in airflow, air infiltration, I should be calling it. If you did all that and you tape to the top plate and you tape to the bottom plate, you get an 82% reduction. So for the sake of a little bit more tape and maybe thinking about taping as well as taping the wrap and to penetration, think about taping to the top plate. That's easy to do. Another couple of rolls of tape will usually do it, maybe 4 rolls. And taping to the bottom. Just make sure that if you're taping to the bottom, you're thinking about your drainage, and you may be taping it to the flashing layer at the bottom, so water can still go down and run off whatever drainage and doesn't run underneath your bottom plate. But it does make a difference. The second layer is your bulk insulation layer. So insulation is actually really easy. The rules of insulation, the hard part is the installation, which Sean will talk about. If we're talking about where you should start as far as insulation, people often ask me, well, how much insulation should I put in? And the answer is as much as you can. As a general, well, no, that's not the answer. The answer is the more the better. Sort of like a water tank, how big should my water tank be? Well, the bigger the better, then it'll catch those big storms. But most of the time you're only using the first 5,000 litres or so of water in the tank, and most of the time the tank's empty. It's the same with insulation. You can, the more you put on, the better, but there's a diminishing return. So you get a lot of bang for your buck for the first R1 that you put in. For the next R1, you get like half the bang for the buck as the first one. For the next R1 after that, you get half as much return. It stops as much as the one before it. Basically, there are diminishing returns. So these tend to be pretty cost-effective sizes to put in, and also work with standard construction cavity spaces. So what will I put in? On the roof, usually has a bit more space, so typically I'll go for an R4. And these, by the way, are what I will put in, whether we design 7 stars, 8 stars, or even 9-star homes. Typically, they'll have this as the specification. R4 for the ceilings. We also put a fallback blanket typically over the top, so that does bump it up a bit. Roof insulation can be a bit higher than wall insulation because heat's trying to rise all the time. So it's a bit more, you do get a bit more bang for your buck for thicker ceiling insulation. But for the walls, not so much heat is trying to get out sideways. R2.5 is pretty good, fits within a 90mm cavity space. Could up that to R2.7. And under the floor, R2.5 tends to be enough, or tends to be, to do well. If you can bump that up, what I'm saying is you just don't get a big performance increase in your NatHERS software. For instance, with that house that I just that I showed you the floor plan before, 8.1. If we made all the walls 140 mil and we put in R4 bats, that goes up to 8.3. So 0.2 of a star difference. Yeah, that's good, but maybe not worth it from a cost-effective point of view. Those are the rules of putting in insulation. Sean will go over that. The main one, of course, is don't have gaps and cracks. You'll see here between these jam studs, we've got the insulation running down. Most building sites would have just left that open. It does make a difference. Fill up, don't have gaps and cracks. And the other thing that's quite important is that your insulation sits flush with the face of the stud, so that when you put your plasterboard on, there's not a big gap behind it. If there's a big gap and there's leaks somewhere, you may find that you get airflow coming, circumventing, going through any leak past the insulation and running down between the insulation and the plaster. And so effectively that insulation isn't working for you. So if you make it flush and the plaster sits back against it, there's not that air gap for that pathway to happen. The last layer of insulation is the tightness layer. And for standard construction, that's plasterboard. If I was doing a passive house, that would be lined with internal membranes. But for standard construction, you can get a hell of a long way just by trying to limit the amount of holes in the plasterboard. Plasterboard itself is fantastic air barrier, especially once it's painted. It's the gaps and cracks in it that let it down. So things like square set cornice, fantastic joins that last well over time for stopping airflow, and try not to have too many lights and things hanging down. You know, don't have banks of downlights with holes cut through it, that sort of thing. But Sean will go over all of those. So I'm just pointing that out to you now. The reason it's important though, why am I banging on about tightness? The reason it's important is that the NatHERS software, you see this red line here? NatHERS software assumes that if we do have a 50 Pascal load of a difference in air pressure between the inside and the outside of the house, it assumes a 10 air changes per hour at 50 Pascals of pressure. That's what the software assumes. So really, as one of your contractual documents, you should be designing a home that is less than 10 air changes per hour at 50 Pascals of pressure. Now, not many people test their homes. And the CSIRO did a test back in 2015 on new home construction in different cities around Australia. For Melbourne, this is what they found. They found that the average air changes in new homes was an average of 15.4 air changes per hour. So technically, they're not actually meeting the NatHERS rating there. There's a couple of other lines that I've got here. There's 5 air changes per hour. Now, if you do get a house down below 5 air changes per hour, there does become a point where the house needs more fresh air to come in, because if it's just a sealed box and you're breathing and living in that space, you can have, you know, undesirable chemicals building up in that space. So you do need some fresh air to come in. So under 5 air changes per hour, heat recovery ventilation is required. And this line down the bottom, this is passive house at 0.6, extremely tight, but they designed from the very start to include heat recovery ventilation. So that's all sorted in there. But the main point is we want to, we might not need to get down to here, but we definitely need to get under 10 air changes as an industry. So generally houses need to be tightened. To give you a little bit of idea of how this affects the star rating, just say you had a 7-star home at 10 air changes per hour at 50 Pascals. Well, at the moment, if you're just building to the average, you'd only actually be getting that to 6.3. So there's a danger there. There's a risk for builders that a savvy owner could potentially take you to task under consumer affairs legislation. And of course, up here at 4.6, your home's not going to be performing at 7 stars if it's that loose. And if you go tighter, you can actually get a little bit of benefit. So interesting to point out. It's reasonably easy, or you can make a big impact on the tightness of a new home by simply caulking, gap filling, putting on extraction fans that don't duct straight to the roof space, but duct to the outside and have backflow dampers on them. And by the way, that's coming in NCC 2022 as a requirement. But these things do make a big difference on your tightness levels. Another thing to point out where a building can potentially fail is with thermal bridging. So Sean will talk about this, but I just want to touch on when I get my my engineering plans, what I'm looking for is there any steel that passes from the inside to the outside? The reason why is that steel is extremely conductive. In fact, compared to softwood, I've got down here, steel is approximately 500 times more conductive than wood. That's hardwood. Compared to softwood, it's more like 1,000 times. So if you have steel on the inside of your house that passes through to the outside of the house, that could be just leaking heat out when you want it to stay in. It could be bringing heat in when you don't want it inside. And it can potentially ruin the star rating or the lived experience of the clients there. So, sorry, what I asked myself is this: have I checked my structure for thermal bridging? That's simply a nice question to ask when you get your plans back. Is there any steel passing from the inside to the outside? If there is, you want to make sure there's some sort of break or it's wrapped around with some insulation or something.
Sorry, Jeremy,
yep.
Just a good question to put in there, and I'm not sure whether you know, but is floor insulation required between a basement car park and the unit or the floor above?
It's a performance standard, NatHERS, so it's not required. Hang on, this might be outside of NatHERS. There may be fire prevention reasons that you'd be putting insulation in an apartment situation. So check that. That's more, you look in the construction manual. However,
I know in terms of thermal bridging, we have had reports of first floor apartments having condensation under the carpets because they're pretty much fitted over a cold concrete floor. So the temperature of the concrete under the carpet is much colder than the temperature inside the unit, and so moisture in the air condenses under the carpet. So that's a really good reason to insulate the roof of the car park, if you like. And I have seen that done in a couple of places I've visited recently.
I'll just finish that my thought. So NatHERS is a performance software. It doesn't give you any rules. However, you're not going to perform well. It's not going to get to 7 stars in a house with an underground car park, say, if you don't insulate above that and the rooms. You're going to have those issues that Phil talked about there. Apartments have more problems going on because it's an average rating that you have to require. So some apartments can be under a 6 star at the moment and scrape in there.
Yeah, and again, because they're pretty much concrete slab construction, most of them, they're kind of inherently tighter as well.
Yeah.
From an energy efficiency point of view, once we've ducted the exhaust fans externally, should the roof space still be ventilated?
From an energy efficiency point of view, no. from a potential buildup of condensation, maybe. It depends on your climate, and the National Construction Code is also bringing in a lot of measures to address condensation, and one of those will be ventilation to the roof cavity. And so let's see what comes out in 2022, whether that gets through. But there were proposals to make sure that roof spaces are ventilated, and it is the norm that happens in most places around the world. So my guess is that it will come here in one form or another.
Yeah, and I guess that, if we've insulated that ceiling correctly and but done it fairly airtight, then there should be sort of the roof space should be separate from the internal environment.
Yes, correct.
In terms of energy efficiency, yeah,
definitely. In terms of energy efficiency, you really want the still air spaces. So there is a little bit of a, you're sort of fighting a little bit against each other, ventilating a roof and trying to insulate and having it still in there. So there will need to be some reasonable details coming out of how to go about achieving both of those aims at once there. Yep. But definitely the less gaps and cracks you have in your plasterboard, the less and the more that you exhaust all of your high loaded moisture sources. So showers have a good extraction fan to the outside, cooking have a good extraction fan to the outside, and have good breathable membranes on the walls. Personally, in my own structures, we don't have all that much ventilation in the roof space, but we haven't had any issues, and that's because we have very few penetrations through that plaster, and there's not much humidity build up in the home, and a good way for it to get out through the walls. So anyway, that's my thoughts there.
And just another thermal bridging one. There is a requirement for steel frame and thermal bridging.
Is that a question or a comment?
I think there is a requirement now to put in.
Yeah, you're exactly right. Correct. Again, it's not part of, not really part of the NatHERS software, but in the National Construction Code, they have they've realized that steel frames bridge a lot more than timber frames do. And so they are bringing in requirements if you use certain structure ways of constructing things. Yeah, they're bringing in thermal break rules about that.
Yeah, and I think Sean will talk a little bit more about this as well. But yeah, that idea that we're sticking in insulation in the cavities, but we've got pretty much a thermal bridge between the outside and the inside.
Yeah, that's right. It doesn't make sense to put plasterboard on one side and direct fix a cladding on the other side of a steel frame and put some insulation in the walls, because the heat's just going to go through every single stud instead. Yeah.
And yeah, I guess this question too. Yeah, we've had this before too. How does all this apply to renovation and extensions? Yes, so some existing homes are pretty ordinary to start with. So, and I guess, look, I'll let you answer that.
Well, this is potentially difficult. At the moment, my understanding is it will be exactly the same as it is now. If you renovate over 50% of the area of a home at the moment, you have to get the whole home up to 6 stars, but the building surveyor does have some say over whether whether it's cost effective to do it or not. They have some control. And it will be a similar case with 7 stars, I believe. Though, from my own personal experience, to get a home to 7 stars, you really need to take off the cladding and re-insulate the existing walls sort of to get there. Yeah. And I know the VBA is working on it, redoing the practice note, because it's sort of started to get a little bit complicated and confusing. So they are working on improving the practice note, hopefully. So we'll see how that comes in the next few months as well. Yeah. Design Matters have been doing a lot of work on rewriting what was a pretty hard to read document.
We've been talking to the same people. Also, can you apply a passive house extension to an existing dwelling that is not passive house?
Of course. Yeah.
It doesn't make the whole house passive house.
Yeah. Obviously, the more surface area you've got at the join, the more you've got to sort of work on that join. If it's only a smaller area, it's a lot easier. But yes, there's no reason why you can't have a passive house part and then a non-passive house part if you want to go down the passive house route. Yep. Actually, when I design, sometimes I over-design the extension part to maybe get a little bit, to get more heat than it needs in summer, because it's linking with the existing part, which is a bit of a drag and often a bit cold, and that extra heat sort of helps to bring the existing home up a bit as well. Yeah,
and I know, using as an example, and I know you don't usually do this, but I'm going to bring it up. You did an extension a while ago in Coburg where you pretty much brought the pretty average house right up to, was it 6 or 7 then?
No, 7. Yeah, over 7.
Yeah,
we've done that quite a few times. Yeah.
And it started with at around,
oh gosh, 2.5, something like that. Maybe. Yeah. So look, you can definitely do it, but it does become a bit of a labour of love, especially on those inner Melbourne homes. There's not much crawl space under floors often. Good job for an apprentice, and make sure they've got a mobile phone with them so they can call for help.
So I rope to their leg or something.
Yeah, something like that. Check in on them every now and again. Yeah.
Of course, we wouldn't ask you to not abide by any occupational health and safety standards.
No, 400 mils, everyone, is what you should be having underneath the bearer to think about insulating underneath the floor.
Yeah, great. Thanks very much, Jeremy.
All right. Here we're actually looking at insulating underneath the slab floor, and I just mentioned this just because in our climate, you don't necessarily need a slab to get to 7 stars by any means, but if you are doing a slab floor in and around Melbourne, maybe as you move up north in the state, less important. But our ground temperatures can get a little bit low here, and if you put a bit of insulation under that floor, it's just easier for the house to heat up in winter, and you'll see that reflected in around about a 0.5 star increase typically in the average home of putting some insulation under a slab floor. In this case, it was waffle slab. But before you do it, it's easy to know, is it good or not? You just check with the thermal performance assessor when you get your assessment done. And it's very easy for them, if you've got a slab floor, just ask them, if I put some insulation under this floor, what performance am I going to get? You know, what star rating is that going to give me? And if it's good for you, then you can talk to clients and maybe do it. All right, so that's basically all you need to know about insulation. Of course, the installation of the insulation is the trick there, and Sean will cover a bit of that next week. So we're on to, we've done looking at laying out the home, choosing good windows, working out how much to put where, eaves, insulating well, some general insulation levels. And by the way, the thermal performance assessor can test those insulation levels. You can start with those general ones that I noted there. And then if there's more space, you can ask the insulation, well, what if we do put R6 bats in the roof? And they'll can give you some feedback pretty easily on that. Now we get on to rule 4, which is thermal mass. And you don't need to have thermal mass to get 7 stars, but again, it will give a little bit of a performance boost on the home, and it'll just make it a little bit easier to get there. The way I think of thermal mass is this. In a lightweight home, you've got energy that will come through those windows if you've designed them right in winter, and the home will heat up pretty quickly. You've got good insulation that'll hold it in, but the home can only hold so much heat. What will happen is it will heat up quickly during the day, and it'll just start to radiate. The whole house will get warm and it'll radiate that heat away. And then when the sun goes down, even though you've got good insulation, it's not holding very much heat within it, and it will cool down reasonably quickly. If you put some mass in that home, it's a little bit like having a glass of water and you're pouring water in. That's the energy coming into the home. A glass of water can only hold so much energy, but if you put some mass in the home, you can now hold a lot more energy. It's a bit like turning that glass into a bucket. It can hold more water, it can hold more energy, or turning into a bathtub. Depending on how much mass you put in. So potentially useful. The most cost-effective way to put in mass is with a slab throughout, because it spreads that mass evenly throughout the house in a reasonably cost-effective manner. So in this particular house, we had some reverse brick veneer going on, which we often include. Now, the way that mass works, this is your typical, you've probably seen these sorts of diagrams before, but this is how it works, and it does work like this. If you've got some mass in the home, here you've got a concrete slab floor, and you've designed so the winter sun can come in under the eave into that home, you're now got the capacity to absorb that heat all during the day. And you've insulated well so that when that sun goes down, that mass holds that heat, and then that mass, starts radiating that heat out. The mass will heat it up to somewhere around 20 degrees during the day. It'll just radiate 20 degrees at you. It'll be quite nice, and it will limit the time at which the heaters need to come on to provide that extra heating in the home. It will sort of decrease the timing that your heaters run. And in summer, it has the opposite effect. If you've designed your eave so you keep out the summer sun, you've insulated the home well, what will happen is, even if you've insulated it well, little packets of heat will finally get through, over a period of time. Doesn't matter how well you do the insulation, you can't stop the heat coming in eventually. But when it does, it's now met with a lot of mass, and it takes a lot of those packets of heat to heat up each degree of temperature gain within the house if you've got a bit of mass in there. And so it will basically keep you cooler for longer in that place. So the question is, how much mass and where? And to answer this question, I would always check with a thermal performance assessor on this. I think a slab is a general good rule, especially if you've got northern windows. That'll be no issue. But when you start putting in internal mass, and here we've got a lot of recycled brick going on, some on that wall painted out, some on that back wall, some here, fair bit of mass going on. This is one of our 9-star homes. And we find that we can get homes quite easily to, high 7s, 8 stars, 8.5 with lightweight construction. But to get it into those very high ratings, a bit of internal mass does help. However, there's a cost benefit analysis that you want to do at this stage. And that's why it's a good idea to check with your thermal performance assessor, should I put a heavy weight internal wall in, and where should I put it? And how big is it going to be, and then you can work out whether it's going to be a cost-effective strategy for you. The other thing, I've got a little note here: consider embodied carbon. With a lot of massive objects, bricks and so forth, they've often been fired in a kiln, and they've got a lot of energy that's gone into them, and so a lot of carbon has been released in just making them. Same with the cement. Takes a lot of carbon dioxide. Well, a lot of carbon dioxide gets released in the creation of cement. So you may very well find, if you're also looking at the embodied carbon point of view, and NatHERS doesn't do this, but you might also find that the operational savings of putting in some mass and getting a bit of a bump in your energy rating is not enough over the life of the house to offset the energy that's gone into it from a purely green point of view. From a comfort point of view, of course, not a bad thing. So yes, that's the question I asked myself about mass. If anything more than your standard floor there. And by the way, here we've limited the embodied carbon by choosing recycled bricks, and the cement in the floor here is 60% of that cement's been taken out and replaced with slag and fly ash, called the triple blend mix. So very low in carbon for a concrete. And little tip here: if you're close to 7 stars or just under the line, you might also want to start playing around with colors, because a darker color floor, if it's a heavyweight floor, will absorb better than a lighter floor. You might have stood on the black road and the white paint. You know, when you're crossing the road with bare feet, you want to stand on the white on a hot summer's day, because the black burns your feet off, because it absorbs more of the energy.
Just a couple of questions, Jeremy, around that.
Yep.
Do floor coverings affect the ability to make use of thermal mass?
They do. They do. So they don't decrease it completely, but they will limit, depending on the thickness and the insulation performance of that. So if you're doing a carpet with a thick underlay, well, you might have almost stayed with a timber floor and it would have been the same sort of performance. But if you were doing an engineered floor and it's just direct fixed to the slab, or glued down to the slab or something, and it's pretty dense material, you'll still get a reasonable performance out of the slab. Or if you do tiles, that's pretty much exactly the same sort of cementitious material, and so that performs fine on slab.
So is that part of the energy rating?
Yep. All those things go into the energy rating model. Yeah.
And does rammed earth perform as well as thermal mass?
It performs fantastic as thermal mass. Yeah, it does. If you've got it on external walls, though, just you will want insulation in those rammed earth walls, because they are, if the sun's not shining, they are highly conductive and they will conduct your heat out during winter. So rammed earth walls, you can get internal insulation within that rammed earth if you're doing that on an external wall.
And if you were to put concrete tiles in under a timber floor, would that have any impact?
If they're thick, they'll have some impact, but you're really wanting to get around about 100 mil of sort of concrete thickness to, well, at least 50 mil of thickness to start making a good impact on the thermal performance mass-wise.
And I guess in a similar vein, what about a Hebel floor?
Hebel is about halfway between concrete and timber. Yeah.
And I have seen a house made out of this as well, and an all concrete house, but what about tilt panels?
As long, again, as they've got insulation within them, and you can get ones with internal, 75 mil of internal polystyrene between 2 skins of concrete as a tilt-up panel. Fantastic performance, yeah.
Thank you.
Yeah. Now, if you do put in a little bit of mass and you include, you got photovoltaics on the roof, if you have gone down an all-electric roof, you've got an efficient reverse cycle air conditioner, as I said, you can start considering your house as a bit of a battery. You'll be making heaps of power in summer. Once the sun comes on, you can cool your house down. As soon as the sun stops, you can turn it off, and the good insulation will keep your house cool easily overnight. And it's likewise during the winter. If the sun comes out, if it's a sunny day, you can heat your home up and heat up, in this case, the bricks here and the floor. And again, once the sun goes down, this house will hold the heat easily throughout the night. Okay, so that is mass. Can be a good thing. Check with your thermal performance assessor. Right, rule number 5 is harness, and this is the last rule, by the way, harness the breeze to keep you cool. And this is really about looking at where your breezes are blowing on summer afternoons. That's when you want to try and get a bit of cooling. Well, summer mornings, I guess, as well, as long as the breeze is cool. And this, what you're looking at now, is the wind roses for Melbourne. And you can see here in Melbourne at 9 a.m. this is in January in Melbourne, at 9 a.m. the wind's blowing from all different directions, but by 3 p.m. it all straightens up, typically, often, into a southerly breeze, quite a reasonable strength too in a lot of areas. Less so as you go further inland. Now, if you don't already know when you're designing or the house you're looking at where its summer breezes are, you can go to this Bureau of Meteorology website down here, and I believe that you'll have access to these slides later if you want to pull out that link. But you can go to that and you can find your local weather station and close to where you're designing or where the house is, and you can find out yourself and get your own wind roses and download them. Now, once you've got that information, oh, well, actually, before we get to that, with breeze paths, it's as simple as just designing wherever that breeze is coming from, designing so that breeze can blow through your house. You don't want this sort of situation where there's one opening and then the breeze can't go anywhere. It's not going to come in. It's not going to want to come in. Similarly to before, where I was talking about plaster as a tightness membrane. If you've got plaster and it's reasonably tight on the inside, even if you've got gaps and cracks on the outside, the air's not going to want to come in because it's got nowhere to go. So for your breeze path, you actually want it to be able to come in and go through. So you want to have an opening on the other side of, 2 openings in a room, or, down a corridor and then on the other room, not too far away. You don't want the breeze to go in and out, have to go in and out too much. It wants to be easy for it to get through. You can induce breeze. If you've got high light windows, hot air naturally rises, will draw in wind from the outside or draw in breeze from the outside. If there is none, if there's no prevailing breeze, it will draw some in and replace your hot air with cool air. And fans also, they don't actually technically cool anything, but they blow air across your skin, which evaporates moisture off your skin and gives you a 3-degree cooling effect locally on yourself. And lastly, don't forget casement windows on the sides of homes. If you've lined up the breeze path and you've done openings on either side of the breeze path, the windows on the side of the home, if you have them with casement, you can sort of angle them so they're all open to scoop in that prevailing summer breeze. Nice little tip. And yeah, so here's an example of breeze paths blowing through the average home. You can see that it's nice and easy for the breeze to get through and blow across the living spaces where people are in summer. This is a 3D of the same house there. And once again, I just imagine I'm the wind, just like I imagined I was the sun when I'm looking at plans, and I'm saying to myself, is it easy to get in and out in the direction that I want to travel? In my prevailing direction that I want to travel, will be easy for me to blow in and out. And am I blowing across where people live in summer? If yes, then that's a big tick. Now, it should be said for because we're in Victoria, most of the time we're heating and not so much in cooling. This will be lovely for people living there in summer, and you'll get a bit of advantage in the NatHERS software, but you don't get a huge amount of advantage because for most of the year we're trying to have our homes a bit more closed and we're heating instead of trying to get that cooling. This would be different if you're designing for up in the tropics where you're trying to cool all the time. Then breeze paths become much more important within the NatHERS software. But still, for just comfort, living in homes with a good breeze path is great when that breeze comes through. All right, so those are all the rules of passive solar design, and that is the level of knowledge that you need to actually work with passive solar design. You don't need to know anymore because the thermal performance software does all the calculations for you. All you need to do is to understand the logic of what you're trying to achieve, and as long as each one of those rules, you're sort of giving it a bit of a tick, doesn't have to be 100% tick, 70% tick is fine. Then you'll definitely, when you do get your rating done, you'll be 7 stars or above typically to start with. So the next step is to use First Rate 5 or any of the NatHERS tools as a design tool to further improve the rating. And For those people who don't know what thermal performance assessors actually do, what they do is they will get the plans given to them by the builder or often by the builder when they're going to get their building permit. At the very end, the building surveyor will say, have you had a house energy rating? And they'll say, oh, no, not. Send off to the house energy rater or through the designer, either way. But what the thermal performance assessor does is they sit down with the plans and they enter all the plan details into the software. And that is floor areas, wall areas, ceiling areas, what floors and walls and ceilings are made of, what they're finished with, timber floors, carpets, what insulation is in the walls, floors and ceilings, what type of windows, where eaves, what things are outside overshadowing, where the other buildings are providing shadows on. Everything goes into the model, and then the model looks at uses the postcode to pull up the local weather data for the last 30 years of weather, and uses that to simulate a calculation for every half an hour for every day over 365 days. Then it will look at what the predicted temperatures are in each room of the home, and it will work out if those temperatures are not in a nice that 20 degree or so band. It will work out how much energy needs to be put in to bring it into a comfort zone, and then it will then work out how much energy the house uses and stick it in the star band. And that's basically how it works. And what it does give a thermal performance assessor, it gives them the opportunity, should you want to do it, to use the software as a design tool. So at the moment, 99% of the industry uses it as a compliance tool just before you get the building permit. However, it was originally envisaged as a design aid. And so what you can do is once you put the data into the tool, the thermal performance assessor can look at the different rooms of the house and can say to himself, well, in this instance, for instance, the rumpus TV area is using a lot of energy per square meter. What's going on there? That's not going on in, the kitchen, dining, or one of the other rooms. And you can start playing with variables. You can say, well, maybe the window's too big, or maybe I've got to put the eave out a little bit more, or maybe it's getting too cold in winter and we've got to pull it back, or there's a tree outside that we might want to look at trimming off some branches or lopping it off to get that sunlight shining into the house. So there's different things you can play with. Should I put in more mass? Should I put in less? And if there are any thermal performance assessors listening, I would suggest as we move into 7 stars, there's going to be a transition period. I assume that I don't know this, but I assume that there's going to be a transition period of at least 12 months. In that time, designers and builders who are involved in design should be working on getting all their designs 7 stars or above. And thermal performance assessors really should be offering the service of what I call an optimization report at concept stage. And so how this would work is a designer would do, and this is exactly what we do in our own office, we do the concept design, and at that stage we do a rating on the concept design. And that way I can, and that's actually my job in the office, and I can say, well, these are the things we can do this is how the house is likely to perform, and this is things we can do to improve it further. And then we talk to the clients, these are the costs of those things. And then the client makes some decisions on how they, where they want to include those and lift their star rating even higher. But that would be a very useful report that could be, it's definitely going to save whatever extra cost that is. It's going to save the householder a lot on operating costs over the life of the home. So it can be sold to them in that way. But anyway, that would be my recommendation for any thermal performance assessors listening to this, that they might want to start thinking about how they would do such a report and how they would charge for it. It does mean at the end, there's still going to be that compliance report where there'll be changes between those concept stage and final stage. So it is an extra charge, but I think one well worth doing. Okay, so that is everything to do with the thermal performance. And if you've done it right, if you've designed right and it gets built right, well, effectively you've knocked off, that a third of the pie has been knocked off. But now you can see, if you look at this pie graph, we've still got 2/3 of the pie left. And this is why whole of home is so useful because thermal performance can only go so far, whereas whole of home looks at each area of that pie graph, and we can address each area to really minimize the energy use in the home. And the first area to address is we've knocked off most of the space conditioning, but there's still space conditioning needed. Now, we can provide that amount of space conditioning efficiently or inefficiently. In this house, we use reverse cycle air conditioning. We actually use heat pump hydronics as well. They liked hydronics. We didn't need both, but they liked the hydronics during the winter. So in the tool itself, these are the options that you get to put in. You get to put in ducted reverse cycle, ducted gas, gas hydronic, room reverse cycle, room gas, electric panels, slow combustion, wood, in slab electric. And for cooling, you get ducted refrigerative, ducted evaporative, and just room refrigerative if you're just doing individual rooms. And there's a little note down here that the whole of house proposed benchmark is a 3-star ducted heat pump. So that's what you want to get at least as good as a 3-star ducted heat pump through the home. And I want to talk to you a little bit about heat pumps because we use a lot of them, and we always choose where we can reverse cycle air conditioning or in this case heat pump hydronics. They're both heat pumps. Reverse cycle air conditioning is a heat pump. And even if you might have heard the word heat shifter, that's another heat pump. These are all different words for this heat pump technology. So what you're looking at now is a standard split system. That's another different word for a heat pump. And the split system has an internal head where it blows the heat and the cool, and then has an external compressor motor on the outside. And it's worthwhile explaining and knowing how these things work, because this is, again, along with photovoltaics, this is one of the technologies that makes net zero a possibility. And what happens is there's a loop of pipe that runs around between the internal and the external head. And inside of that pipe is a refrigerant. It's a gas. And what happens is, so let's say this is in heating mode. What happens is the gas comes down here to the outside and goes through this thing called an expansion valve, and that expands the gas. Whenever you expand the gas, whenever you expand the gas, it gets cold. So you might have felt this if you're doing the car tire, blowing up the car tire, and you feel the gas thing rushes on your hand at the petrol station. It's quite cold. Or if you're trying to do up the barbecue gas bottle and it rushes on your hand, quite cold, because that's compressed gas that's expanding out and becomes cold. And in fact, it becomes around about negative 40 or so degrees. Someone might correct me on that, but it's cold. And on the outside of your house at night time, it might be 0 degrees. It might be -5 degrees on a cold night. But compared to negative 40, it's still hot. There's still heat in the air to grab. And so there's a big fan that blows that night air or the outside air across the pipes. And the heat goes from the air into that negative 40 pipe, into that negative 40 refrigerant. It goes around, comes through here and goes through the compressor. And the compressor squashes it. Whenever you squash a gas, it does the opposite. It gets hot. And you would have felt this if you ever pumped up a bike tire with a hand pump. As you're pumping away, the hand at the bottom starts to get very hot because you're squashing air down that end. And the refrigerant is now very hot, and it goes inside. It goes through little thin pipes, copper pipes in the head unit, and a fan blows that heat into the room. And then that cools down the refrigerant in the pipe. It now goes outside, gets expanded, and it soaks up some heat on the outside, brings it back in, compresses it, and blows the heat out into the side. So what's happening is it's actually not making any heat. It's just shifting heat. That's why it's sometimes called a heat shifter, from the outside to the inside in this case. And in the cooling mode, it's shifting it, it's grabbing it, it's running the opposite direction. It's just grabbing the heat from the inside and coming in and dumping it on the outside. Now, why are these things so amazing? If I wanted to heat my home with a gas system, say, the most efficient that gas system could be, the most efficient I can get on the market at the moment is around about 93% efficient. That means the gas is burned in the furnace, and 93% of the heat gets through all the ducting through the roof and then into the home. That's pretty efficient for a ducted heat system. These things, though, these heat pumps, they start at around about 300% efficient and go up to the best ones are pushing 600% efficient. And that sounds crazy. It sounds against the laws of thermodynamics. But the reason is because they're not actually making any heat. They're just shifting it. So for every kilowatt hour this thing runs for, if this is a base sort of line one, it will be shifting around about 3 kilowatt hours of heat from the outside to the inside. And that ratio of 1 kilowatt hour of energy to run, shifting 3 kilowatt hours of heat, that's called its coefficient of performance. So COP stands for coefficient of performance. If it's shifting 4 kilowatt hours of heat for every 1 kilowatt hour that it runs, it's got a COP of 4. And EER stands for energy efficiency ratio. This is the number when it's in cooling mode. If it's cooling, it's shifting the heat from the inside to the outside and therefore over time cooling the inside. Its acronym is EER, but it's exactly the same thing. It's a ratio of how much energy it takes to run versus how much energy it shifts. Now, with split systems, you don't just have to have single splits. There are also multi-splits. You can have one, which is one motor, one compressor, running multiple heads in the homes. And they can be cassette types, wall types, ones that you build into bulkheads is just sort of vents in the wall, even radiator type panels. Or you can do a reverse cycle ducted system, which is the benchmark product of 3-star version of that. They're less efficient typically because of the ductwork. You lose a lot of heat to the attic with ductwork. Now, whatever you're choosing, when you're choosing, you should be trying to choose the highest stars that you can. As simple as that. And that's what gets entered in the tool. So if you were choosing and want to stay, you want to use gas, no problem. Just choose the highest gas stars. With electric reverse cycle air conditioners, however, there's a little bit of trick at the moment because they're changing over from the old star system, which is this one, which you're used to a new label, which is called the Zoned Energy Rating Label, or the ZERL. And the difference is with these old star ratings, they did one test at one temperature in one climate and then gave it a rating. And it's simply not the case that the same air conditioner will perform as well in a humid climate as it will in an alpine climate, say. And so different technology perform better in different areas for reverse cycle air conditioning. So they've now split it into three different climates: black, grey, and white there. And you simply choose where you are and then read off the label. And the more stars, the better there. You can, of course, go straight to the specifications of any of the heat pump systems. And what you're looking for is this little line where it says energy efficiency ratio or coefficient performance, cooler heat, and that's the number you want to read off. So this is a super efficient one. For every kilowatt hour of energy it used, it actually shifted almost 6 kilowatt hours of heat. All right. So if you are using heat pumps.
Sorry, Jeremy, just a quick one. We're coming up to time, so.
Yep. Yeah, I know, because we were doing some questions before. So how do you want me to proceed?
How much longer do you think we've got?
The last part is reasonably quick compared to the first half. I reckon we've got another 15 minutes.
Okay, look, we'll keep going. If people can stay, that'd be great. We just had a couple of quick questions too while we're there.
Go for
it. Best sort of split systems you specify?
The best sort, the ones with the highest coefficient of performance, and then the best feature set on them. You've got ones these days that can have what they call the magic eye, and they can see where people are in the room. In heating mode, it will blow air away from those people, so you don't feel, cooled down by airflow. In cooling mode, it will blow air at those people, so you get even, more cooling effect. So that's a good one. And they can also, some of them can self-clean, some of them destroy VOCs. They've got some technology that destroy volatile organic compounds in the air to have a pure indoor atmosphere. A lot of good technology there. Yeah,
and some control humidity and those sorts of things as
Correct,
well.
yes,
so,
humidity control is a big one. Yep.
And ducted heating units, should they be insulated? For ducted heating, should the ducts be insulated?
Yeah, don't go for minimums. I would go for, sort of the maximum that you can duct up there instead of going, 0.6, R.6 or something. Or I'm not sure what the minimums are these days with ducting, but choose an R2 or something, something significant, because you're putting very hot air through there into potentially a cold roof space. That's a good way to increase the performance, is increasing the insulation around the ductwork.
Yeah, I think mine's heating a couple of cats under my floor somewhere. But anyway.
yeah. Check them every now and again.
And Susan says, look, keep going. This is great.
Thanks, Susan. All right. So, assuming you are using heat pumps, if you're using ducted, or standard ways of heating and cooling, yeah, that's about how much energy you're going to use. But assuming you're using heat pumps, you can effectively provide this wedge of heating and cooling with a fraction of the power. If it's got a coefficient performance of 3, it's about a third of the power. So whammo. And we've almost knocked off half of the pie of the standard home. All right, water heating. Let's get into water heating. With water heating, these are the two technologies that I'd be looking at if you wanted to provide your water heating and do it with a lot less energy than is in that particular wedge. There's the two technologies. One is the good old solar hot water, still work extremely well. To actually get on the list of the rebate list, you have, as a solar hot water manufacturer, you have to have a unit that provides at least 60% of the hot water by the sun heating it over a year. So, and the best go up to around about 75, pushing 80% of your hot water is provided by the sun. So it's still a very good option. Over here on the left, you'll notice something that looks pretty similar to a heat pump. And because it's a heat pump hot water system. And once again, you can get heat pump hot water systems with a coefficient performance around about 4. So effectively, you can provide your hot water with, almost a quarter of the power. So both these technologies extremely good. The other one that's not part of the whole of home under the NCC at the moment is shower heads. But don't forget, in a house, 50% of your hot water goes to your shower. So if you put in an efficient efficient shower head, you just use less hot water. So you save energy that way. And still, as long as it's a nice shower head, you don't lose any function out of that. In the tool itself, you get to put in solar gas boosted, solar electric off peak, electric storage, basically all the types of hot water that you can think of there. The benchmark appliance is a 5-star instantaneous gas heater on the outside, so reasonably efficient gas heater. If you are wanting to choose solar hot water or a heat pump, this is not a bad website to know about. It's the REC registry for called the STC calculator, the small scale technology certificates. But basically all solar hot water systems and heat pump systems that get rebates on them, and in Victoria they're getting rebates at the moment. To get that rebate, they need to put their efficiency, and they need to have their efficiency tested, and the more STCs that you get means it was a more efficient system. And you can actually go and you can scroll through the different options, different models and things that have been rated there. So just another good resource when you're choosing efficiency of solar hot water or heat pumps. The more STCs, the more efficient the system. Yep. And assuming that you choose one of these two technologies, you can provide that much hot water with a fraction of the energy. So that's the sort of saving you get. These are all just indicative, but they give you a sense of the benefit. Lighting's only a small wedge, but it's easy to pick up some points here, because once again, this is compared to all existing homes. And if you're doing a new home, most homes these days are going to be LEDs. As long as you do LEDs, you'll get a bit of a saving on this wedge. The other thing is, if you can have lights that hang down into the space, you can have less of them to light a room. So general rule of thumb is that one pendant light effectively gives out the same amount of light as 4 downlights, because they're much more directional. They don't spread the lighting as much. What I've noted here, the whole of house proposed benchmark is 4 watts. So if you're under 4 watts, you'll get a bit of a bump in your whole of home assessment. And assuming you do that, and the other good thing, if you have banks of downlight, like I said before, your plaster layer is then a lot more leaky, and your thermal performance will go down. And that is actually recognised in the NatHERS tool. You have to enter in the NatHERS tool how many downlights there are and whether they're sealed or unsealed. So anyway, if you avoid them completely, you'll have a tighter structure and you'll get a saving on your lighting wedge. Approximately that much, around about 40%. Cooking. Now, cooking, like I said...
Sorry, Jeremy, just a quick one about hot water.
Yes.
And it's one I thought about myself as well. Can you have solar preheating a heat pump hot water heater? Are there any like that?
So I've asked this question myself, and the answer is yes, you could, but at the moment, the heat pump manufacturers, I think it voids the warranty of hot water feeding into them.
Mm-hmm.
So you could, and that would be probably the most efficient, but it's also a pretty costly way to do it. And you've already got a big gain either going solar hot water or just going heat pump to start with. So you're sort of going for the nth little bit of extra performance by merging them together there for the extra $4,000 or something that you'd have to pay. Thanks. Yep. Or might not be 4,000, maybe extra $2,000. But either way, that's my answer there. Cooking. So cooking is not part at the moment, like I said, of the National Construction Code proposals in the 2022 version of the energy improvements. However, if you change your gas cooktop for an induction cooktop, you get a little bit of saving, because your gas, when you heat things with gas, a lot of that goes around the sides of your pots and pans, whereas induction cooktop, it all goes into the pans, much more efficient. So you get a little bit of saving there. But really, the biggest benefit of doing this is that this is often the last gas appliance in the home. And if you get rid of this, you can go all electric. And then you can get rid of the gas meter, and you can save, your $300 or so a year of connection fee for the life of the house, and the charge of running a gas cable, a gas line. So potentially a big benefit. And the other thing for the owner, they then only have one bill to look at. They don't have a gas bill. And if you're trying to work out how much energy you use, it's really hard. You've got megajoules and got kilowatt hours and two different bills and trying to work it out. So it does make things a lot easier for owners to manage their energy. In the tool itself, you've got gas, electric, or induction for cooktop, and the electric is just a resistance electric heater, your old coil type system. Oven, you've got gas or electric. But assuming you go induction, you'll get a little bit of saving in that cooking wedge. And you see how we're starting to really eat away at the energy used in the pie, in the average home there. And the last wedge is the appliances. And like I said, the electricity consumption is calculated automatically based on the average new appliances for your house size. So they do look at the size of the home, how many room bedrooms it has, how many people are likely to live in there when they're looking at the load of appliances. However, if you can convince your owners, your clients, the owners of the home, to actually just choose the high stars. It's as simple as that. When they go shopping for, for refrigerators and TVs, especially those two, they can use a huge amount of power, especially the big TVs these days. If they're choosing the higher stars, it doesn't have to be the top star, but one or two from the top, that'll make a big saving. Each one of those stars is a 25% improvement around about on the star before it. And for some of these bigger white goods, you save around about $50 a year each time you go up to a higher star just in running costs. So it does make a difference. And especially if you've gone this far and you've done all this for the client to get a really efficient home, let them know. And I often just give them a list of efficient appliances that I've used before and say, these are things that I recommend. And often when they go away shopping, they come back with half of those things on their list and say, yeah, we're happy with those. And the ones that they change, they often change out for similar efficient sort of models. So reasonably easy to get some leverage there. If you do that, yes, you get a bit of a saving there on that wedge. It's not more than that because there's a lot of other things that get plugged into homes over time, phone chargers and consoles and so forth. The last thing that gets entered into the Sustainability Victoria tool is the pool, if you have one. you would tick yes, and then you get to choose, well, under the National Construction Code proposal, all you're needing to enter is whether you've got a single stage, a dual stage, or a multi-stage pump. They all use slightly different amounts of power. But in the Sustainability Victoria version tool, you can actually put in some details about the type of heating if you want to get more of a realistic how much energy this home is going to use. And that is it for the tool. The very last piece of the puzzle is to include solar and potentially car charging. So we've eaten away a huge amount. We've probably taken 2/3 of this pie away just by efficiency measures. How much do we now need to offset to provide the power to just provide for these wedges that are left in that pie there? And the Sustainability Victoria tool allows you to enter in different sizes, and you can put in batteries as well if you want to put in batteries, that question before. And then you can use that data, and it will let you know when you press compute whether your house is producing as much power as it's going to need over a year, over a 12-month period. So you can use the tool that way. What we've found ourselves, we've probably been building net zero homes. Our first one was back in 2012 when our owner brought us their bills and said, look at this. So we've found if we take this whole of home approach, put in efficient appliances, most homes start breaking even somewhere around 5 kilowatts a panel or so, depending on the size of the home there. So yeah, just something to consider. And when you consider that the average standard system size that's going in at the moment is 6.6 kilowatts, this is a potentially very realistic pathway for the industry to go. And we could be one of the first industries potentially to move to net zero, if we push all this through. Last thing is car charging, not part of the National Construction Code at the moment, but all the homes we're building these days, the garages we're building will definitely have electric cars in them within the next decade or two. So we may as well set up for them because it's really easy to do. What you want to do is just, what we do and what I'm recommending to all clients and builders is just to put in a 32 amp cable that allows for fast charging if the house goes to 3-phase, but it also works if it stays on single phase. It gives enough capacity, and I just put it in the wall to wherever a charging point is likely to be. Take it back and terminate it just behind the switchboard. Leave a couple of slots in the switchboard ready for switches later. And now I'm actually also putting in a conduit, just an electrical conduit with a pull string, taking the same route, so that potentially there's this thing coming out called V2H and V2G, vehicle to house and vehicle to grid protocol. And they're looking at this as an idea of when the car is home, it can be the battery for the house. So the house can actually, the solar panels can feed into the car and the car can feed back to the house at nighttime. Car batteries, sorry, they're going a long time. Car batteries are extremely large. They're around about 3 times as large typically as these Tesla batteries that you're seeing on the house there. And if they can talk to each other, all the better. So that conduit is really just so you can potentially put some sort of, cable through so that it can talk back to the house. A couple of things to note, nice little factoid here. When you're thinking about solar panel size and how much roof space to allow, if you allow somewhere between 5 and 6.8 square meters of roof per kilowatt of panel, depending on the efficiency of the panel, for roof size when you're laying out, if you're thinking to yourself, well, I'm going to put on at least 6.6 kilowatts, maybe typically I like to put on at least 8 these days, just give a bit of capacity. That will tell you how much roof space you need. And last thing to consider is that the average car, if you do want to allow for car charging, the average car drives around 50 kilometers a day. More in the country, yes, but 50 kilometers a day, to charge a battery to run an electric car for 50 kilometers a day, it works out that an extra 2 kilowatts of panel would be all you need to, on average, provide enough power for that 50 kilometer a day travel for an electric car. So you might want to add on another 2 kilowatts. As-built verification, I did say I was going to talk about this very briefly. as we move to high performance and as we're potentially promising homes that use little energy to run, we want to make sure that our build quality meets the design criteria and the requirements under NatHERS of that 10 air changes, and then the insulation is in well. And Sean will talk about this a lot more, but it really doesn't take long to teach a team. If you get a blower door test done, and that's a picture of a blower door there, and you get your team on site, you know, one afternoon of them walking around with the house under pressure, feeling where the air is coming in through gaps and cracks, that'll be enough to really improve standards. The other thing that's a fantastic tool for site managers is a little addition that can go onto a phone or onto a laptop or a pad, and it just turns it into a thermal imaging camera. If you take a few photos like this and you show your trades that you can see behind the plasterwork, you can bet that they will make sure that they put plaster back if they've put bats back if they've had to move them when they're doing some work. So it really improves standards very quickly. And Sustainability Victoria put out a fantastic little as-built verification fact sheet and checklist. So definitely look out for that. Lastly, we've done all this work. What can be achieved? Well, 7-star passive solar design, you get high performance construction with the detailed insulation. Basically, you get a very comfortable environment. The temperature can be going up and down outside, but inside you're going to have a much more stable environment inside. You're also going to get, potentially, if you put in double glazing and you've done your insulation well and you minimize gaps and cracks, it's going to be a very quiet house. It's going to be a bit of sanctuary from the outside. Home energy bills, of course, if you saw originally the average house, $2,300 or so in electricity and gas bill, if you put them together, well, you can minimize most of that and have really just the connection fee and maybe a third of that bill left over. So that's a lot of money for the owner to save ongoing over the years. And lastly, of course, we're doing this for the environment, and we now have the technology, we have the know-how, we have this new Sustainability Victoria whole of home tool. We basically have what we need at the moment to get our industry to net zero and save those 8 tons of carbon being emitted in the atmosphere every year. All right, so that's it, Phil. I don't know if there's any questions left or whether to end it, but I'll leave that to you. Thanks.
Great, thanks very much, Jeremy. No questions at the moment. But look, thanks very much for the presentation. You know, having done this myself, I know it's really hard sort of sitting in a room all by yourself talking to a screen.
Yeah.
But, you know, hopefully, again, you know, it looks like there were some really good questions, lots of good information for people. And it looks like most people have hung around to the end as well. So, yeah, we got some people sort of thanking you as well through the Q&A at the moment. So thanks very much, Jeremy. Yeah, Bianca, I'll just check with you. Is there anything else we need to do?
Thanks, Phil. No, nothing else we need to do. Just to let everyone know, we do have that webinar next week, which you mentioned earlier on the 11th. So if you are interested, please make sure to register on our website, as spots are limited. So the exact same way you registered for today, make sure you do that for next week. But otherwise, that's me, Phil. Anything else, Jeremy or Phil? All good?
No, that's it. Thanks anyone who's hung around this far. It was a bit of an arduous journey, but I think it's useful seeing it all in one hit like that, so you understand the entirety of it.
So, sorry, Jeremy, just a couple of questions that are popping up. So I'll just quickly go through them. There was something else I wanted to say as well, but okay. We will send you, give us a few days, but we will send you a copy of the presentation and, you know, fact sheets and a copy of the webinar as well. So just give us a few days and we'll set that out for you. Where can they get or you look at the software for the whole of home?
You would want to contact Sustainability Victoria.
Yeah.
For that. In fact, on the information sheet that they will get, there is a link.
There's a link to that. Excellent. Okay, great. Yep, look, great session. Excellent, informative. Thank you very much. First rate 5 tool, is that available to anyone? Well, it is, but you've got to pay for it. So
great.
And But you know, energy rater will able, you know, if you get yourself a good energy rater, and we've talked about this for years as well, especially as these, you know, as the requirements get tougher, a good energy rater is worth probably every few dollars more that you might pay them versus someone else. So, yeah. Look, very informative. The building link for next week is online, is available on the Master Builders website site. So if you go there, you should be able to register there. I know a few people had some issues, but I think we've sorted those out as well. So thanks very much, Jeremy. Registered, but no link for next week. Okay, we'll find out what's going there. Excellent presentation. Yeah, we will send all the slides and what have you. Thanks very much, Jeremy. A list of energy raters available through
Design Matters National. Go to Design Matters National, Google that, and you can find a list, and you can even search by location and stuff. So, yep.
Yeah. Okay. So look, thanks very much, everybody, again for coming along. Keep an eye out. We're in the final stages of confirming our date for our Green Living Conference this year. So I'm very excited if we can have that in person. So keep an eye out for that over the next few weeks as well. But yeah, thanks very much, Jeremy, and thanks very much, Bianca, for helping organise all this, and the team at Master Builders behind the scenes as well for organising all the registrations and what have you. Thanks very much, everyone. We'll end it now.